Can you hear me? Can you hear my voice? Yes, what about others? Okay, I think you can hear my voice clearly. Assalamu alaikum wa rahmatullahi wa barakatuhu. Bismillahirrahmanirrahim. So this is our sixth week virtual session. And in continuation to the previous lecture, in this session we will discuss about access method of standard Ethernet. Okay, so we have discussed the addressing. Now we will discuss access method. So the standard Ethernet uses CSMA-CD with one persistent method. Okay, and this thing we have discussed in the previous virtual session when we were discussing about MAC, Media Access Control. You remember one persistent method? We have discussed about one persistent method, non-persistent and P-persistent method. Remember? What do you mean by one persistent method? Yes, anyone? What do you mean by one persistent method? Unicast. Say one persistent method. In this method, okay, what happens? When the station finds that the line is idle, then what it does, it sends its frame immediately with probability of 1. Okay, so we have a link, number of stations are connected to that link. Okay, number of stations are connected to that link. So what a station does in one persistent method, the station senses the line, and if it finds that the line is idle, what it will do, it will send the frame immediately with a probability of 1. Yes, the sender. So when we are talking about standard Ethernet, it uses access method as CSMA-CD with one persistent method. Now the next is implementation. So standard Ethernet defines several implementation, and only 4 of them became popular. We will see it in table. What are the 4 standard Ethernet implementations? They are TenBaseS, 10base2, 10base-T, and 10base-F. Now, if we see this nomenclature, what we have, it has 10, then base, and then X. Okay, now you can see over here. This is 10 base, okay, 10 base, 10 base, and 10 base. Now we have X. This X varies. In first case, X is 5. In second case, X is 2, then we have T, and then we have F. So in this nomenclature, what does 10 represent? 10 represents the data rate, okay, 10 Mbps. This is the data rate. Now next we have base. Base means baseband signal, or we can say digital signal, baseband digital signal. And now this X defines either the maximum size of the cable in meters. For example, if we have 10^5, that means 500 meters. The length of cable is 500 meters. Or it defines the type of cable, which type of cable we have. Like in this case, here we have T and F. That means the cable is twisted pair, and F means it is fiber optics. So the standard Ethernet uses a baseband signal. As you can see, we have 10 base, which means that the bits are changed to a digital signal and directly sent on the line. So here we have 10^5. The medium is thick coaxial cable. And in 10^2, the medium is thin coaxial cable. In 10^T, as we know, T stands for twisted pair. So in this case, the twisted pair cable is UTP, unshielded twisted pair. And we have 2 pairs of UTP. And in 10^F, we have 2 pairs of fiber optic cable. These are the medium length, 500 meters, 185 meters, 100 meters, and 2000 meters. And the encoding that we are using is Manchester encoding. So this encoding is in chapter number 4 because it was not in your course, so that's why we have not discussed encoding schemes. Otherwise, if you want to study it, you can study it from chapter number 4. Now, let me give you a brief introduction. What do you mean by Manchester encoding? In Manchester encoding, 0 is represented like this. This is for 0. And 1 is represented like this. Okay? This is for 1. Now, if we are transmitting a signal, okay, suppose I want to transmit 0, 1, 1, 0. Now, if I'm using Manchester encoding, as you can see, for 0 we have this signal. So what will happen? It will be like this for 0. Then for 1, it will be like this. Again 1, so it is like this. And 0, that means it's like this. So this is Manchester encoding. I have given you just a quick overview of what Manchester encoding is. Now here, in this diagram, you can see that all standard implementations use digital signaling, that is baseband at 10 megabits per second. So at the sender side, data is converted to a digital signal using Manchester scheme. As you can see, we have Manchester encoder over here at the sender side. And at the receiver side, the received signal is interpreted and decoded into data by using Manchester decoder. So Manchester encoding is self-synchronous and it provides a transition at each bit level, or we can say at each bit interval.
Now we will discuss these implementations one by one. So the first one was TenBaseS implementation. This implementation is also called thick Ethernet or thicknet. So this name thick Ethernet or thicknet basically derived from the size of the cable. Okay, if you will see this cable is thick and it is too stiff to bend with your hands. So TenBaseS was the first Ethernet specification to use a bus topology with an external transceiver. So we have a transceiver over here. Now transceiver means that it is a transmitter as well as receiver. So the function of transceiver is it is used for transmitting, receiving and detecting collisions. So this transceiver is connected to the station via a transceiver cable that provides separate path for sending and receiving. This means that collision can only happen in the coaxial cable. Now the maximum length of the coaxial cable is 500 meters. Okay, and now if this cable exceeds beyond 500 meters, then there is excessive degradation of the signal. So the size of cable should not be more than 500 meters. Now if a length of more than 500 meters is needed, okay, so up to 5 segments, each a maximum of 500 meters can be connected using repeaters. So this concept of repeaters we will discuss in chapter number 17. Okay, when we will discuss chapter number 17, we will discuss about repeaters. Now the next implementation is TenBaseS implementation. It is also called thin Ethernet or thinnet or cheaper net. So TenBaseS uses bus topology, but the cable is much thinner and it is more flexible, as you can see over here. So this cable can be bent to pass very close to the stations. So in this case, the transceiver is a part of network interface card which is installed inside the station. Now this implementation is more cost effective than TenBaseS because the thin coaxial cable is less expensive than thick coaxial cable, and here we have T connections instead of taps. Like in this case, these are the taps. And T connections are much cheaper than taps. Now as far as installation is concerned, installation is simpler because the thin coaxial cable is very flexible. Now the length of each segment cannot exceed 185 meters. It is close to 200 meters due to the high level of attenuation in thin coaxial cable. Now the next implementation is TenBaseS, or we can say twisted pair Ethernet. So TenBaseS uses a physical star topology. The stations are connected to a hub via 2 pairs of twisted cable. Now here the two pairs of twisted cable create two paths, one for sending and one for receiving, between the station and the hub. So any collision which happens here is in the hub. So compared to TenBaseS or TenBaseS, we can see that the hub actually replaces the coaxial cable as far as a collision is concerned. Now the maximum length of the twisted cable is defined as 100 meter to minimize the effect of attenuation in the twisted cable. And the last implementation is TenBaseS implementation. So TenBaseS uses a star topology to connect stations to a hub. This is a hub. And the stations are connected to the hub using two fiber optic cables. So this was all about standard Ethernet. We have discussed about the addressing, access method, and the implementations. Now, after standard Ethernet, other Ethernets also came into existence. We will discuss them one by one. But before we discuss higher rate Ethernet protocols, we should discuss the changes that occurred to 10 megabits per second standard Ethernet. So these changes actually opened the road to the evolution of the Ethernet to become compatible with other high data rate lengths. So what were the changes? So in this figure, you can see that the first step in the Ethernet evolution was the division of a LAN by bridges. So bridges have two effects on an Ethernet LAN. They raise the bandwidth and they separate the collision domains. So in unbridged Ethernet network, the total capacity is 10 megabits per second, and it is shared among all the stations with a frame to send. The stations share the bandwidth of the network. If only one station has frame to send, it benefits from the total capacity of 10 megabits per second. But if more than one station needs to use the network, the capacity is shared. So for example, if two stations have lot of frames to send, they probably alternate in usage. So when one station is sending, the other one refrains from sending. So we can say that in this case, each station on average sends at a rate of 5 megabits per second. Now in this figure, you will see a network with and without a bridge. So another advantage of a bridge is the separation of collision domain. So in this figure, it shows the collision domain for an unbridged and a bridged network. So you can see that the collision domain becomes much smaller and the probability of collision is reduced tremendously in this figure. So without bridging, 12 stations contend for access to the medium, and with bridging, only 3 stations contend for access to the medium. Now next is switched Ethernet. So the idea of a bridged LAN can be extended to a switched Ethernet. So instead of having 2 to 4 networks, we have N networks, where N is the number of stations on the LAN. So a layer 2 switch is an N-port bridge with additional sophistication that allows faster handling of packets. So evolution from a bridged Ethernet to a switched Ethernet was a big step that opened the way to an even faster Ethernet. As you can see in this figure, now one of the limitations of TenBaseS and TenBaseS is that communication is half duplex. So a station can either send or receive, but may not do both at the same time. So the next step in the evolution was to move from switched Ethernet to full duplex switched Ethernet. So this figure shows you a switched Ethernet in full duplex mode. So information can be transmitted and it is received at the same time. So in full duplex switched Ethernet, there is no need for CSMA-CD method. In a full duplex switched Ethernet, each station is connected to the switch via 2 separate links. Each station or switch can send and receive independently without worrying about collision. So each link is a point-to-point dedicated path between the station and the switch. So there is no longer a need for carrier sensing. There is no longer a need for collision detection. The job of the MAC layer becomes much simpler and easier over here. The carrier sensing and collision detection functionalities of the MAC sublayer can be turned off. So now we have fast Ethernet. As you can see, the bandwidth of fast Ethernet is 100 megabits per second. So the designers of fast Ethernet needed to make it compatible with the standard Ethernet. So the MAC sublayer was left unchanged which means that the frame format and the maximum and minimum size would also remain unchanged. So by increasing the transmission rate, features of standard Ethernet that depends on the transmission rate, access method, and implementation had to be reconsidered. So the goal of fast Ethernet was to upgrade the data rate to 100 megabits per second and to make it compatible with standard Ethernet. It has another feature called auto negotiation. So this feature allows a station or a hub a range of capabilities. It allows two devices to negotiate the mode or the data rate of operation. It was designed to allow incompatible devices to connect to one another. For example, a device with a maximum data rate of 10 Mbps can communicate with a device with 100 megabits per second data rate. So to allow incompatible devices to connect to one another, we have a feature called auto negotiation. Now next is Gigabit Ethernet. Here the bandwidth is 1 Gbps or 1000 megabits per second. And here also we have this feature called auto negotiation. Now first of all, we will consider fast Ethernet. Now in case of fast Ethernet, we will see that there are three implementations. We have 100 base TX, we have 100 base FX and 100 base T4. So 100 base TX uses two pairs of twisted pair cable. It may be either category 5 UTP or STP. So for this implementation, MLT3 scheme was selected. As you can see, in encoding, we have MLT3 and 4B5B. Now, this encoding is not in your course, okay? But if you want to study it, you can study from chapter number 4. It's based on encoding. So there are a number of encoding schemes. We have RZ, return to 0 encoding. We have NRZ, not return to 0. Then we have Manchester encoding. We have MLT encoding. So these encodings you can study from chapter number 4. So here MLT3 is not a self-synchronous line coding scheme, and 4B, 5B block coding is used to provide bit synchronization by preventing the occurrence of long consequences or long sequences of zeros and ones. So this creates a data rate of 125 megabits per second, which is fed into MLT3 for encoding. Then next we have 100 base FX. It uses two pairs of fiber optic cables. So optical fiber can easily handle high bandwidth requirements by using simple encoding schemes. So the designers of 100 base FX selected NRZI encoding scheme for this implementation. So NRZI has a bit synchronization problem for long consequences of zeros or ones based on encoding. So to overcome this problem, the designers use 4B, 5B block encoding. So the block encoding increases the bit rate from 100 to 125 megabits per second, which can easily be handled by fiber optic cable. And then we have 100 base T4. So 100 base T4 was designed to use category 3 or higher UTP. The implementation uses 4 pairs of UTP for transmitting 100 megabits per second. So encoding, decoding in 100 base T4 is more complicated, as this implementation uses category 3 UTP, and each twisted pair cannot easily handle more than 25 M baud. So in this design, one pair switches between sending and receiving. So 3 pairs of UTP category 3, however, can handle. So we need to use an encoding scheme that converts 100 megabits per second. So in 8B60 encoding scheme, 8 data elements are encoded as 6 signal elements. Now next we have questions will be from this table. We may ask for the implementations of fast Ethernet. So you have to name the implementations. Okay. We can ask for medium, which type of medium we are using for which implementation. Then the medium length. So these questions can be in multiple choice question or in true and false or fill in the blanks. Okay, or a short answer type question can be given to you, which may ask about medium, medium length, wires, encoding. So this table you have to memorize, this table. Okay. Similarly, the previous table that we have discussed for standard Ethernet, like this one, this table you should memorize. What are the 4 different implementations for standard Ethernet, which medium we are using, what is the medium length, and what encoding we prefer. Yes. Now it's clear? Is my voice clear now? So we have discussed about fast Ethernet, and now next comes Gigabit Ethernet. So the need for even higher data rate resulted in the design of Gigabit Ethernet protocol. That means 1000 megabits per second. So the goal of Gigabit Ethernet was to upgrade the data rate to 1 Gbps, but it was a major concern that we have to keep the address length, the frame format, and the maximum and minimum frame length the same. So the goal of Gigabit Ethernet was to upgrade the data rate to 1 gigabits per second and to make it compatible with standard and fast Ethernet. Now these are the 4 implementations for Gigabit Ethernet. The first one is 1000BASE-SX. Now here SX it's also called shortwave. As you can see, we have fiber SW, that means shortwave, and we have 1000BASE-LX. The medium is fiber LW, that means long wave. Then we have 1000BASE-CX, that is STP. And the 4-wire version uses category 5 twisted pair cable, that is 1000 base T4. Short wave, it's for short wave. Short wave. So 1000 base T4 was designed as response to those users who had already installed the wiring for other purposes such as fast Ethernet or telephone services. Now we have Gigabit Ethernet. So in 10 Gigabit Ethernet, the idea is to extend the technology, the data rate and the coverage distance so that the Ethernet can be used as LAN and MAN. So the IEEE committee created 10 Gigabit Ethernet and called it standard 802.3 AE. So the goal of 10 Gigabit Ethernet design can be summarized as upgrading the data rate to 10 gigabits per second, keeping the same frame size and format, and allowing the interconnection of LANs, MANs, and WAN possible. So this data rate is possible only with fiber optic technology. So that's why if you see here, the medium that we are using in this case all are fiber optics. So the 4 implementations for the Gigabit Ethernet are 10 G-base SR, 10 G-base LR, 10 G-base EW, and 10 G-base X4. Now the medium length for these implementations are 300 meters, 10 kilometers, 40 kilometers, and 300 meters to 10 kilometers respectively. Number of wires that we are using are 2, and the encoding is 64B, 66B, SONET, and 8B, 10B respectively. So with this we came to an end. So in this lecture we have discussed about wired LAN. Wired LAN, that means Ethernet. And we have seen the 4 generations of Ethernet. We have discussed their implementation, their media access control, access method, their addressing, and the different types of implementations. If you have any question, you may ask. We still have time. Now, as far as your midterm is concerned, instead of in week 8, your midterm is in week 9. So I think all of you have this information that your midterm will commence from 6th of November. Their chapters will be up to chapter number 13. Course will be up to chapter number 13. Ethernet use in the building. Ethernet use in the building means you want to say in LAN. In LAN we use Ethernet. Can you please make it more specific? What do you mean by Same building. The same as before. Yes, the chapter number 13. That is wired LAN. LAN and MAN. Yes. Yes, Ethernets are used in LAN and MAN. When I started teaching you this chapter, I have mentioned you that in case of Ethernet, in case of IEEE project 802, okay, we have seen that in TCP/IP protocol suite also we have seen that when we consider physical layer and data link layer, there are no protocols associated with these two layers. The TCP/IP protocol suite accepts any protocol which will provide functionality to the network layer. So whenever we are talking about physical layer and data link layer, we are talking about the type of network. Okay, which type of network is using it? So it can be LAN or it can be MAN, local area network or metropolitan area network. So I'm still here. If you have any question, you may ask. Otherwise, we will meet in next face-to-face lecture, inshallah. Till then, take care, all of you. Assalamu alaikum.